Hello guys, so welcome to Thursday lecture, and today we're going to continue our discussion about MOSFET amplifiers. We already discussed last lecture about common source amplifiers, in which you have the input is at the gate and the output is at the drain, and the source is just common between them. And here is the equivalent circuit for it. After our analysis, we found that EV is equal to minus GMRD. So we can control this EV to make it with high value if we control RD and also the biasing, which will determine GM. Our input is infinite, which is very good. And RO is equal to RD, which is from moderate to high values. And one note here is that you can say, okay, I will increase RD to increase EV. But then you should remember that if you increase RD, yes, EV will increase, but RO will increase as well. So it's a trade-off here, okay? You can't just go with any value for RD. Okay, so let's now continue the discussion with another two configurations, which are the common gate and the common drain amplifiers. So let's start by common gate amplifier, in which the input is at the source and the output is at the drain here, and the gate is just common between them. Okay, so let's draw the equivalent circuit for it. You know, guys, we take two equivalent circuits and we say that both are equivalent, just like BGT, and you can use any of them. It's usually better here to use a second version in which the gate is at the bottom and you have the source on the left and the drain on the right. So here is the equivalent circuit. Here you have the gate, and remember that the gate has all the time a gate current equal to 0. Okay, so whenever it's connected here, the current into the gate is 0. And you have here GM VGS, and here is the drain, and here is the source, and this is 1 over GM. Okay. And remember, the polarity of VGS is in that way. The positive is always near the gate, and the negative is also. So because it's called VGS, the voltage of the gate with reference to the source. The source is negative. Okay, good. So let's continue the rest of the circuit. Between the source and the ground, there is our signal and V signal. And remember, the input is just at the terminals of the signal, and here is also our input from that location. And the gate is connected to ground, and the drain is connected to the ground through RD. And that's it. And here is VO. Okay, let's determine EV first. So EV is equal to VO over V input. VO is the current through RD, which is GM VGS. And remember, this current is flowing from bottom to up, so it's an opposite polarity with VO. So it's minus GM VGS RD over V input. And the input is just equal to the gate source voltage, or the source gate voltage in that case. So it's minus VGS. Remember, VGS is positive negative, but V input is positive, positive negative, and V input is positive negative. So it's opposite. So minus will go with the minus, VGS will go with VGS. So it's GM RD. So first observation here so number one, same as common source amplifier gain in amplitude, but it's non-inverting, which is good, non-inverting. Also, most of the cases, we don't care about the inversion of the output signal. And non-inverting means there is no phase shift. Remember, with common source, the AV was minus GM RD. So the output is out of phase with the input. Good. And this is also good, good amplification. Just like common source. So let's determine our input now. Number 2, our input. Our input is just, V input over I input. And I just assume this is I input here. So it's basically 1 over Gm. So the resistance between the source and the ground is just 1 over Gm. And this is usually, here is the observation, low input resistance. So it's not, till this moment, not inverting, which is good, good gain, okay, but it has low input resistance, different from the common gate amplifier, common source amplifier, I'm sorry. Okay, number 3, RO. So for RO, we remove the load. Basically, we don't have a load here. I mean, separate load. Okay. So if we draw the circuit after putting, Vx and Ix as usual, we have RD. Then we have our GM-VGS. And we have here 1 over Gm. And we have our signal, and we're gonna cancel the source, the independent source. So ROA is equal to Vx over Ix. Okay. When you cancel the source here, which is V signal, basically VGS will be equal to 0. Okay. Because the current here is equal to, since there is no source, the source is 0 now. So 0 over the resistances, which is R signal plus I1 over Gm, is equal to 0. So V signal is equal to 0. So Gm, VGS is equal to 0, or open circuit. So Vx over Ix is just equal to Rd. And here is the observation now. This is moderate to high resistance. So that till this moment, we didn't gain anything useful, okay? Because basically this is has lower input resistance than a common source amplifier, okay? Same output resistance, same amplification. Yes, it's non-inverting, but most of the time the inversion, doesn't affect us so much, and we can just ignore it for most of the applications. But we lose something. We lose our input. But turns out that there is some applications, like the example we're going to see today, in which you need input resistance. Okay. For example, when you interface with a coaxial cable, if you guys study this in field theory, when you have a coaxial cable, you need a proper termination for it. So you need a load resistance, which has resistance equal to the equivalent resistance of the coaxial cable, so that there will be no reflections. Okay, so for such applications, we will need common gate amplifiers or common base, which is the corresponding one in BJT transistors. Both have very low input resistance, but it's beneficial for such applications. Okay, let's now go to the common drain amplifiers. So this is the last, last configuration we have. So with common drain amplifiers, we have the input is at the gate, as we see here. The output is at the source, and the drain is just common between them. Okay. So let's draw the equivalent circuit and see. So I'm gonna solve this particular example using two solutions, and basically they will merge to the same stuff, because basically it's the same circuit. Okay, so I will gonna solve it first using the first equivalent circuit that we used to do. Then the other version of the equivalency, just to show you that if you use both, okay, the problem may get harder or easier, but you should get to the same conclusions or the same, you know, numbers. So let's do it first with the first equivalent circuit, the one we just used to do. Okay, so let's do it first. So solution 1. So this is here is, sorry, the source. Here is the gate, here is the drain. GM VGS. And here is VGS. And it's open circuit between the gate and the source. So the source is connected to RL like this. And here is VO. The drain is connected to ground. And the gate is connected to our signal, V signal. And where is the input? The input is in the terminals of the signal. So between the gate and the ground. So this is the input. Okay, and of course, these are the two terminals from which we get our input. And here is our output between this terminal and this terminal. Good. So let's do our analysis now. So AV number 1, AV, VO over V input. Okay, VO is equal to the current here multiplied by the resistance RL. The current is GM VG because this current just, you know, it's open circuit here, so all of it will go to the RL. So here is GM VGS RL over V input. V input is from that loop. It's equal to V output plus VGS. So it's equal to VGS plus V output, and V output is GM VGS RL. So VGS with VGS will go away. So AV is equal to RL over RL plus 1 over GM. Usually, let's write it, you know, usually RL is much greater than 1 over GM. And remember, 1 over GM is the input resistance of common gate amplifier, and we say that it's low. Okay, it's usually very low. So RL usually much larger than 1 over GM, and in that case, RL plus 1 over GM approximately equal to RL, and in that case, so EV will approximately equal to 1. And here is some observations on that. So basically, no amplification. Although it's called amplifier, but there is no amplification. Actually, it's attenuation. It's a slight attenuation as the output. Because this is basically less than 1. But since 1 over GM is much less than RL, most of the cases, so it's approximately 1. Okay? It's non-inverting, which is good. Because it's a positive. So the output has the same phase shift as the input. And since it's 1, since VO is at the source and the input is at the gate, we call it source follower. Just like common collector amplifier. We call it emitter follower. Okay, because the voltage output is at the emitter and approximately equal to the voltage input at the base, so we call it emitter follower. Okay, here is exactly the same. And we will see in a moment it's the same characteristics as well. Okay, so tells it, and by the way, EV now is approximately 1, and also common collector has approximately 1 for EV. So let's go to the R input now. Number 2. R input. So R input basically is V input over I input. It's equal to infinity because I input is 0. It's open circuit here. Open circuit, which is very good. And remember also, common collector amplifier or the emitter follower has also very high input resistance. Okay, so far so good. Let's now see RO. So we're gonna remove RL and put VX and IX and see, and of course cancel the source. So we have here grounds in GM VGS, and here is VX, and here is IX. Oh, sorry, IX, and I'm gonna cancel the source. So we have something like this. This is our signal, and here is VGS. Okay. So RO is equal to VX over IX. Okay, what is VO? So what is VX? From that loop here, VX is in that way, VGS is that way, and let's assume there is a current in our signal in that way as well. So we have VX plus VGS from that loop plus I, let's call it I, multiplied by our signal equal to 0. I is 0. So this term is 0. So basically VX is minus VGS. How about IX? So IX at that node here, the current input is IX. Also GM VGS is also input, so it's also positive, equal to 0. There is no other currents. So from that, IX is equal to minus GM VGS. So let's now compensate in RO. So RO is equal to VX, which is minus VGS, IX, which is minus GM VGS. So minus will go with minus, VGS will go with VGS. So this is 1 over GM. 1 over GM. This is usually very low. Remember, this was the input resistance of common gate. So this is very low input resistance, which is very good. And remember, also common collector amplifier or the emitter follower also has a very low output resistance. So till this moment, we are, have an equivalent version of the emitter follower here, but it's called now source follower with exactly the same characteristics: high input resistance, low output resistance, and AV approximately 1. Okay, and the same applications as well. This will be used again as a buffer, we can say, between very small loads and very and voltage sources with very high internal resistances. Okay, if you remember, guys, this was the application for common collector amplifiers. So let's now solve the same common drain amplifier using the second version of the equivalent circuit of the transistor. And we'll see that they are both equivalent. They will lead the same conclusions or same equations, same numbers. So in the second version, we have the drain, and here is GM VGS. Then you have the gate. Then you have the source here, and between the source and the gate there is 1 over GM. And here is VGS. Okay. And then the gate is connected to our signal, V signal. Then the ground. The drain is connected to the ground. And here is the source. The source is connected to the load. Then the ground. Here is VO between the source and the ground. And here is the input. Remember, the input is between the terminals of the source. This terminal and the ground, the second terminal, including RS, of course. Okay. So let's now, make the analysis again and get EV and R input and R output. Before anything, always the current that flows into the gate is equal to 0. So this current here, I, is equal to 0. This is, essential step. Otherwise, your whole analysis will be wrong. Okay, that's why this is basically equivalent to the first one. The first one you have open circuit. Okay. Good. So AV, number 1, is equal to VO over V input. So what is VO? Let's follow this current. Let's follow the flow of this current. This current, flow in that branch. Then at that point, it should divide. It should go somewhere, some part somewhere, and two branches. So some part will go to the first branch, another part will go to the second. But remember, I is equal to 0. So this current here, let's call it IO, is completely equal to VGS GM. So IO is equal to I plus GM VGS. I is equal to 0, so it's equal to GM VGS. So VO is equal to IORL. IO is GM VGS, and here is RL. How about V input? V input is voltage across from the gate to ground. So from that loop here, V input is equal to VGS plus VO. So it's equal to VGS plus VO, which is GM VGS RL. So EV basically equal to VO, which is GM VGS RL over VGS plus VGS GM RL. VGS will go away, so this will be RL over RL plus 1 over G. Let's check if this is equivalent or not. Here is AV. Yeah. It's exactly the same. RL over RL plus 1 over G. Number 2, our input. Our input is basically V input over I. I is 0. So V input over 0. So it's equal to infinity. And that's why I told you, you remember all the time, if you use this version of the equivalent circuit, to mark this current as 0. Otherwise, you have, a wrong V output, our input here. So now we're going to calculate our output. Okay. Remember again, here is the equivalent circuit after, canceling V input and putting Vx and Ix as usual. Remember that the current that flows to the gate is equal to 0, which is I here. Okay. So what is Vx? From that loop here, let's call it loop 1 or whatever. So Vx plus VGS. Remember, VGS has this direction. Minus I, our signal, equal to 0. Remember, I is equal to 0, so IR signal is equal to 0. So Vx is equal to minus VGS. Now, what is Ix? So here is Ix is going into the gate, and GM VGS is also going into the gate, so minus GM VGS equal to 0, so Ix equal to GM VGS. This is plus, yeah, so this is minus. Both are going into, so both are plus. So Ix is equal to minus GM VGS. So now, based on that, RO is equal to Vx, which is minus VGS, and Ix, which is minus GM VGS. VGS will go VGS, minus with minus, this will be 1 over GM. So let's now compare our input and our output. Our input is infinity, our output is 1 over GM. Our input is infinity, which are right, and our output is 1 over GM. So again, using either versions of the equivalent circuit, either this version or this one, both are equivalent. I'm just showing one example to make you feel comfortable in using any of them. But for some problems, using the second one makes it really easier, especially with common gate amplifiers, or when you have RS resistance between source and the ground. Okay, but especially with most transistors or most amplifiers, the differences are not that high. Okay. Okay, good. So let's now see some examples. Okay, let's first see the comparison between them. So here is just a highlight for the comparison, but again, don't just try to remember these equations here, because these are based on circuits. Remember, a circuit will determine. You should, for each circuit, you should draw the equivalent circuit and try to analyze it. So if you notice here in that table here, there is a note that these values are based on some figures in the book. Okay, but usually, whatever the circuit of common base, or common gate, or common source or common drain, usually have the same characteristics. And I mean by same characteristic, high or low input resistance, high or low output resistance, high or low AV. Okay. So if you guys remember, our AV is for common source with GMRD, our output is RD, and if you add a load, this load will be in parallel with RD, so it will be minus GMRD parallel RL. And GV, which I didn't touch till this moment, okay, it's actually equal to EV multiplied by our input over our input plus our signal. But remember, our input is infinity. So if we just divide these two terms with our input, so our input over our input plus our signal divided by our input, so this will be 1 over 1 plus our signal over our input. Now, if you put our input equal to infinity, this will be 0. So GV will be equal to EV. But again, this is if you based on the biasing circuit. You should do it again, because we will see examples now. Common source, but it has some input resistance, not infinite. Okay, so at that moment, EGV will not be equal to EV. If we add, a resistance RS, which we can call degenerate resistance, okay, which is connected to the source, not the emitter, EV will be, again, our input will be infinity. GM will be reduced a little bit, because we're going to add something in the denominator called the GMRS. And remember, if RS equal to 0, this will go to this. And if there is RL, then you have AV, which is not equal to AV naught at that case. And again, if our input is in infinity, AV will be just equal to GV. Okay. And here is just the two configurations that we just discussed. So the input resistance of common gate is 1 over GM. AV is GM RD. If you have a resistor, a load resistor, it will be GM parallel RD. Okay. And since now our input is 1 over GM, so 1 over GM over 1 over GM plus our signal. So there will be a difference now between GV and AV because our input now is not infinite. The source follower, so which is the common drain. Again, our input is infinity. AV approximately 1. RO is 1 over GM. If you have a resistor or load, this will be the amplification gain. Okay, but I didn't show that, but it's easy to analyze, so I will leave it for you guys. And here is again GV. GV is equal to AV again because our input is infinite. Okay, so let's now take examples. This example is very nice in the book. Okay, it's 2 circuits. You analyze each one first by itself, then you connect them to each other to see the overall amplification and the stuff after connecting them. Of course, if you connect them, they will have multi-stage amplifier. That's why I like to do it. So these are the 2 stages. We're gonna analyze each one by itself, then connect them to make a multi-stage amplifier. Good. So let's solve it. So the NMOS transistor in the source follower here. This is source follower because the input is at the gate, the output is at the source, and the drain is just common. Okay, has a GM equal to 5 milliampere volt squared. I'm sorry, this is just milliampere per volt or milli ohm minus 1 because ohm is volt over ampere. So ampere over volt is ohm minus 1. Find the open circuit EV and RO. Okay. Basically, since there is no load here, so whenever we calculate EV, it will be EV open circuit. Open circuit means our load is equal to infinity, and we have no R load here. Okay. So let's call this RS. Okay. And let's draw the equivalent circuit and analyze the circuit. So we have. So between the source and the ground, there is RS here, which is 10 kilo ohms. The drain is connected to ground. And here is the gate, and here is VGS, the voltage of the open circuit, and here is V input. Okay. And where is V output? V output is the voltage at the source. So this one here. Okay, GM is known, AV and RO. So AV is equal to VO over V input. VO is equal to the current through RS multiplied by RS. What is the current through RS? It's GM VGS. So GM VGS RS. So this current here will just go, all of it will go to RS because it's open circuit. This way is open circuit. And what is V input? V input is the voltage between the gate and the ground, from the gate to ground. So from that loop here, V input is equal to VGS plus VO. So VGS plus VO is GM VGS RS. So AV equal to GM VGS RS over VGS plus GM VGS RS. So this will be equal to RS over 1 over GM plus RS. Similar to what we get, okay, but we call it RL in that case. It was RL over 1 over GM plus RL. Okay. So we know RS, We know GM as well, so we can calculate EV. So EV will be equal to 0.98. As you see here, it's approximately 1, right? That's why you usually, neglect 1 over GM to RS. RL. Okay. Number 2, RO. For RO, we're gonna connect. There is no RL here, by the way. It's just RS. So there is no RL. If there is RL, it will be here. Okay, so we're gonna remove this and put VXIX. So let's do it. So RO will be equal to VX over IX. So let's draw the circuit after putting this VXIX. Here is GM, VGS, here is the ground. And we can cancel the input, so okay, good. So RO is VX over IX. So what is VX? VX from that loop, it's actually the voltage across RS. Okay, so from that loop here, from that point to that point to that point to the ground again. Okay, VX. Let's write it in a better way. Vx plus VGS equal to 0. So Vx is equal to minus VGS. That's good. Now Ix. So at that point here, at that node, Ix is entering the node. GM VGS is also entering the node. And let's assume there is a current here called I, which is going out of the node. And what is I? I is the voltage across RS over RS. What is the voltage across RS? Is Vx. So Vx over RS. So from that, Ix equal to Vx over RS minus GM VGS. And remember, Vx is minus VGS. So this is minus VGS over RS minus GM VGS. So RO equal to Vx is minus VGS. And what is Ix? It's minus VGS over RS minus GM VGS, which is good. All of them are negative because resistance is usually positive. So this will make you sure that you are in the right direction. So the negative will go away. VGS will also go away. So this will be 1 over GM plus RS, plus 1 over RS. I'm sorry. 1 over RS. By the way, this is basically RS parallel or 1 over GM. 1 over GM. Okay, the combination of the two parallel resistances 1 over R equal to 1 over R1 plus 1 over R2. So R total will be 1 over R1 plus 1 over R2. Okay, so 1 over RS plus 1 over GM. So it will be GM. Okay. But anyways, we know GM. GM is 5 milli. We know RS, it's 10 kilo ohm. And remember, they are both, since this is in milli, but it's in numerator, and this is in kilo in the numerator. So overall, they are milli and kilo will cancel each other. So RO will be in kilo. So don't worry about that. So RO, after calculating that, will be equal to 0.196 kilo ohm. Good. Now the second circuit, or the second, let's assume it's a different equation, actually, a different circuit. Okay. So again, GM is equal to 5. Again, this is ampere per volt, not volt square. Find the open circuit EV and R input. Okay, good. So find EV and R input. So basically we're gonna draw the equivalent circuit. Remember here the input is at the gate. Not the gate, I'm sorry. The input is at, sorry, the input is here, is at the source, and the output is at the drain. So it's a common gate amplifier. So this is common gate amplifier. So let's now draw the equivalent circuit. So the equivalent circuit for common gate, we're gonna use the second version of the transistor equivalent circuit. So you have GM VGS, and you have 1 over GM. Between the drain and the ground, there is 5 kilos and the 2 kilos, because of course the capacitor will be short. So we have here, let's call this RD, let's call this RL. RD. And here is VO. VO is between the drain, of course, after in AC, this will be the same point, D and the ground. The gate is connected to ground. Okay. And the source, here is the source, is connected to two things actually. So you have this RS here. And then you have this V input. Okay. Here is VGS. And remember the polarity, positive at the gate, negative at the source. So EV is equal to, where is V input? V input is at terminals of the input, which is here. So this is V input. It's VO over V input. VO is equal to this current multiplied by the parallel combination of RD and RL. And remember, it's negative because this current is flowing from bottom to up. So it's opposite to VO. So minus GM, VGS, RD, parallel RL. And what is V input? Basically, if you take this loop here, V input is just minus VGS. Because VGS is negative at the top, positive at the bottom. V input positive at the top, negative at the bottom. So they are opposite, so it's minus. So AV will be equal to minus GM, VGS, RD over parallel RL, I'm sorry, over minus VGS. So this will go with this will go with this. So this is GM, RD parallel RL. Good. So what is, we know GM, it's 5. We know RD, it's 5 kilo ohms. We know RL, it's also, RL, it's 2 kilo ohms. So EV is equal to, let's check here, 7.15, 7.15. And it's positive. And we know for common gate, the amplification should be positive, non-inverting. So this is EV. How about our input? So our input, it's basically without any complication. You have to remember this circuit here is isolated from this circuit. So our input is just equal to RS parallel 1 over G. If you look between these two terminals, you will find only two resistors, RS and 1 over G, and they are in parallel. So our input is RS parallel 1 over G. You know RS, it's 10 kilo ohms. You know 1 over GM, or you know GM, it's 5. This is the question here, it's 5. So we can determine basically this combination, and this combination will be equal to 0.196 kilo ohms. And by the way, this is basically exactly the same RO of the first. If you go back here, it's exactly the same as RO. So RO of that circuit is equal to our input of that circuit. Okay, good. Now let's see what happens when we connect them to each other. So in C it says if the output of the source follower, this circuit, this is a source follower here, in the common drain is connected to the input of the common gate amplifier. So the output of the source follower is connected to the input of the common gate amplifier. This is the common gate amplifier. Okay, use the results in one of two and the two to obtain the overall voltage gain. Okay, so now they are connected. So let's draw the equivalent circuit of both together, right? So what you're gonna do here is just bring, copy and paste the equivalent circuit of the common drain of the source follower and just connect it to the input. Take the output terminal from this one and connect it to the input terminal of the common gate amplifier equivalent circuit. Okay, I'm gonna draw them from the beginning. That's maybe easier. So the source follower here, this is the equivalent circuit. We have GM VGS. And you have here RS. Okay, this is RS. Let's call it RS1. Let's call this RS2. You have one RD, so call it RD, and here is RL. Then the drain is connected to ground, and here is the input. And the input of the circuit is actually the input of the first stage. Remember, we have two stages now: stage 1, stage 2. So this is actually the input of the first stage. VO1 is actually the input of the second stage, and VO is the output of the second stage as well. And the output is here. So this is VO1. Let's draw the second circuit. The second circuit will be something like this. You have RS. You have 1 over GM. You have VGM, GM VGS. Then you have finally two resistors in parallel. RS2, I'm sorry, RD and RL. This is RS2. Here is the gate, here is the drain 2, gate 2, source 2. And source 2 is connected to the output 1. Okay. Good. So AV, so here is VO2, which is just equal to VO. So AV is equal to VO over V input, okay, which is VO2 over V input 1. Multiply and divide by V input 2. V input 2 over V input 2. We didn't do anything, okay? And remember that V input 2 is actually equal to V output 1. So call this, I'm sorry, VO1, and we'll keep this V input 2. I'm sorry, this is V output 1. This is 1 here. Okay, so good. So EV equal to VO2 over, I'm sorry, so VO1 over V input 2. Yeah, VO2 is equal to V output 1. So equal to V output 2 with V input 2 is EV2, or the amplification of the second stage. And V output 1, this is 1. V output 1 over V input 1 is EV1, is the amplification of the first stage. Where is the first stage here? Here is the first stage. Let's draw them. There is the first stage. Stage 1. Where is the second stage? Here is stage 2. Okay. Good. So to determine EV1 and EV2, okay, so let's do it. So let's start by EV1. EV1 is equal to VO1 over V input 1. Okay. What I'm gonna do now, I'm gonna determine our input of the second stage. So we can remove all the encircled stage 2 here and just put our input 2 instead of it. So the circuit will be something like this. This is our S1 and then our input 2. Okay. And by the way, this is VGS1, you know, VGS2 here. And here is VGS1. And, you know, here is VGS2. But what are input 2? Our input 2, we don't need to calculate it from the beginning because we already did it. So our input 2 or our input of this stage here, this circuit has input resistance of RS parallel 1 over GM, which is 0.196. We did it already. Okay, so we know already our input 2. Some problem here. So our input 2 is 196 kilo ohms. This is from B, from point B. Okay, good. VO1 is equal to, so here is VO1. VO1 is between gate, between this is source 1 and the ground. This is source 1 and the ground. Is equal to the current here, which is GM VGS, multiplied by the parallel combination of RS1 and R input 2. So GM VGS RS1 parallel R input 2. V input 1 is equal to, from that circuit, from that loop here, V input 1 is equal to VGS 1 plus, this is 1, V output 1. And we know V output 1 is that case. So EV is equal to V output 1 GM VGS 1 RS1 parallel R input 2 over VGS 1 plus V output 1 with GM VGS 1 RS1 parallel R input 2. VGS 1 will go away. So basically, this will be the value of AV. We know GM, we know RS1, we know our input 2. So if we compensate here, we're gonna get EV of the first stage. This is AV1. So AV1 will be, let's check here. Yeah, 0.49. Remember, why it decreases? It was 0.98, 0.98. It was approximately equal to 1. What makes it less is that when we connect both together, you know, we add a new resistance in parallel with RS. So this resistance reduces, you know, the gain to 0.5 to 0.49, almost half. It was approximately 1. Now it's approximately half. Okay, why is this again? Because this new added resistance. New added resistance. Okay, that decreases AV. Always RL decreases AV. This can be considered as the load for the first stage. Good. Now let's calculate AV2. AV2 equal to VO2 over V input 1. I'm sorry, V input 2. So let's go back here and see. This should be easy because here is VO2. It's the current through RD and RL. So VO2 equal to minus GM VGS2 RD barrel RL. And V input 1, if we look here carefully at that circuit here, here is, I'm sorry, V input 2, not V input 1. So here is V input 2. If we make a loop here, V input is actually the voltage across 1 over GM, which is minus VGS2. So V input 2, not 1, I'm sorry here, minus VGS2. So EV2 is equal to minus GM VGS2 RD parallel RL over minus VGS2 minus with minus VGS2 is VGS2. This will be GM RD parallel RL. I didn't write GM1 and GM2 because both are equal. Both are 5 milliampere per volt or milli or minus 1. Okay. We know GM, we know RD, we know RL. So if we did the calculation here, this would be 715. Good. Now finally, AV now, which is EV1 multiplied by EV2 is equal to 0.49 multiplied by 715. This will be 3.5. Okay. And what was the requirement here? The requirement was the overall voltage gain. So we did it. Okay. We solved the problem. Okay. That was a very good example because it combines, you know, common drain or the source follower and also common gate in the same example, and also give you an idea about, you know, what will happen if you combine two stages together. You see here that the first stage usually when you do that, when you add a second stage, when you add a load, which is our input of the second stage, its gain will reduce. So it was before adding the second stage, it was approximately 1. It goes to approximately half. Okay, it's attenuated or reduced. Good. So let's take another example here. So here is another example, okay, in which I will explore with you, you know, the application in which we needed really a small input resistance, okay. And as I said, usually this happens when you, you know, interface to, you know, an antenna or, you know, coaxial cable in which you have very low input resistance for such devices, okay. So the equation, you know, I'm sorry, the problem here is that we have two stages. Again, we have first common source amplifier, then we have a common gate amplifier. Common gate amplifier. Okay, and between there is a coaxial cable. Just a cable, okay? But the problem with the coaxial cable, when the signal flows through it, it's usually make, there will be, you know, a kind of, you can say radiation or something. So the radiated signal may make reflections and stuff. So you may have losses inside the coaxial cable. Okay. We will not care about, you know, the internal operation of the coaxial cables right now, but what we need here to know is the equivalent resistance of this coaxial cable. Okay. Because these reflections will be minimized or even reduced to zero if we interface this coaxial cable to a circuit, and this circuit has input resistance equal to the input resistance of the coaxial cable. Okay. So let's read together the problem and see what's really required and what's really given. So this circuit shows the scheme for a coupling and amplifying a high frequency pulse signal. So we have here our input signal, which is high frequency pulse. High frequency usually have you know, radiation and stuff, and reflections. Okay, and of course losses. The circuit utilizes MOSFETs whose bias details are not shown. So these two common gate and the common source circuit has forced the biasing, but the biasing are not shown. Okay, and we will not need it. We have a 50 ohm coaxial cable between the two stages. Okay, and when we say 50 ohm coaxial cable, that means that the input resistance here of that guy is 50 ohm. For proper operation of that circuit, okay, transistor Q2, this is Q2 here, the common gate, is required to present a 50 ohm resistance to the cable. So the input resistance of the second stage here, and remember, common gate means the input is at the source. So here is the source. So when we look between the source and the ground, we should see 50 ohm. If this guy, for example, the coaxial have 100 ohm, so the input resistance of the common gate should be 100 ohm. So to minimize the reflections, or to minimize the losses. Okay. Number one, find GM2. Find GM of that transistor Q2. Okay, so let's do that. Okay. So let's draw the equivalent circuit of the common gate alone, without the coaxial cable or the first stage. So it will be something like this. You have here GM VGS. Here is the drain. Here is the source. Then 1 over GM. And GM2 in that case. And here is the gate. And the gate is connected to ground. Okay. And the drain is connected to ground through RD. And here is VO. Good. So I will not draw the rest of the circuit, which is connected to the source, the coaxial and the first stage. But let's ask ourselves a question here. So what is our input here? So this is our input 2. And we said that it's required for Q2 to have, or the stage 2, to have input resistance equivalent to the resistance of the coaxial cable. So our input 2 is equal to 50 ohm. But what is our input 2 here if we look between these two terminals? This is at the ground. So our input 2 is also equal to 1 over GM2. So 1 over GM2 is equal to 50 ohm. So GM2 is equal to 1 over 50, which is 20, I think, millimho or milli ohm minus 1. Yeah, 20 milli ohm minus 1. Good, that's A. So let's go to B now. If Q1 is biased at the same point as Q2, since they have the same biasing, they should have the same current. So same biasing means same current. So ID1 is equal to ID2. What is the amplitude of the current pulses in the drain of Q1? And here I write it for you guys. I small, D small. Maximum. The amplitude, I mean, the maximum amplitude of the current in Q1. So what's required here is I, D max. Remember, when we amplify something, we have the biasing, which is DC, and superimposed on that DC, there is EC. And what's required here is the maximum current, the maximum AC current, without the portion, the DC portion. Okay, good. So let's go back a little bit and make the analysis again of the small signal inputs. You remember, guys, from not the last lecture, the lecture before the last lecture, we made this analysis. We said that usually the inputs are small in amplitude. So let's see what kind of approximation we can make based on that assumption, which is a correct assumption, a very valid assumption. And we find that we can decouple the DC from AC. So let's do it again. So ID, I small d capital, means AC plus AC, equal to ID1 here, equal to Kn over 2 V small GS capital minus V threshold square. Remember, it's required in that question here ID maximum. ID maximum will happen when the voltage at the gate here go to maximum. So this happens at VG maximum. Remember here Vs is equal to 0 all the time in AC or DC. Okay? So this is equal to Kn over 2. This is VG maximum minus V threshold square equal to Kn over 2 again. And then V small G maximum is V capital, G capital, the biasing voltage, the DC biasing voltage of Q1, plus V small G small, which is V input maximum, by the way. The input here, this is V input, minus V threshold square. Okay, this is equal to Kn over 2 again. And then I will take VG capital, V threshold capital as a one term, and add here VG max square equal to Kn over 2 again. And then, I'm sorry, there is no square here. Then I will make the squaring. So this is VG minus V threshold square plus VG max square plus 2 VG max VG minus V threshold. Okay, this is equal to Kn over 2 multiplied by this guy, VG minus V threshold square plus Kn over 2 VG max square plus 2 Kn, because Kn over 2 multiplied by 2 will go by 2 with half. So Kn VG max VG minus V threshold. Good. What is this? This is ID capital. Okay. This is the biasing current, the DC biasing current of Q1. Plus Kn over 2 VG max square plus Kn VG max. And yeah, and what is Kn VG minus V threshold? This is GM. So the third term, this is GM basically. So the third term will be GM VG max. And remember, for a small signal model, in the small signal, VG max square is assumed to be much smaller than the first term, which is, you know, Vg minus V threshold square. So we can basically neglect Vg max square. So this can be neglected, So based on that, ID, I small d capital equal to ID all capital plus, this will be neglected, GM Vg max. This is DC, and this is pure AC. Okay? So ID, I small, D small max is actually equal to the AC portion, which is GM Vg max. GM is known, 20 millimho, ohm minus 1. Mo is ohm minus 1. Multiplied by Vg max. And what is Vg max? Vg max is, if we look here, it's 5 millivolt. Okay, I remember here there is also milli, so it will be micron. So ID max basically is 0.1 milliampere. That's what's required in B. And C now is connected also to B. So basically the same question, but another, you know, another requirement. So what is the corresponding amplitude in voltage pulse at the drain of Q1? So number C, basically it asks for what is VD max. Now I'm gonna draw again the equivalent circuit of the first stage, because we need only AC voltage here. So gate 1, drain 1. I'm sorry, this is gate 1, here is the source of the gate. So usually common source amplifiers, we draw the original version of the equivalent circuit. Source 1. Source is connected to ground. Between gate and source, there is open circuit and a voltage VGS1. Then you have the input, VG, or VGS, S is 0, so it's VG. Now, between the drain and the ground, we're going to see what we can see. We see here the input resistance of the coaxial cable, or input coaxial. Our input coaxial, which is 50 ohm. So we can just remove the coaxial and, you know, the second stage and put just 50 ohms, and we're fine. And now what's required is VD max, VD1 max. Because again, we are talking about the first stage here. VD1 max. We know ID1 max, which is the current flows here. So ID1 is flowing into our input. So VD max is basically, VD1 max is equal to ID1 max multiplied by our input coaxial. So VD max, equal to 0.1 milliampere multiplied by the 50 ohm. We can leave it by as ohm, and the result will be in millivolt. So this will be 5 millivolt. So there is amplification here. So the input is yeah, this is basically the output, the maximum output that we can see in the common source stage. Okay. Good. Okay, guys, so this is, so next time we're gonna see more example. In our last lecture would be on Tuesday, December 8th. So this lecture will be basically also some review on most transistors. And if you have examples or something or questions, so the last lecture will be a synchronous lecture. And if you have any problems to solve or any kind of question, so you can answer, and I'll also solve 2 more examples on most transistors. Okay, guys, so see you next time.